Okay, our second part of sedimentary rocks. So we, in the first part, talked about weathering, and remember that weathering was different than erosion. So erosion is moving stuff away from where it was weathered. So erosion and transport is going to be moving the material that we're breaking down that's going to become sediment and eventually sedimentary rock. So erosion and transport. Sediment can get transported in a lot of different ways, and I have pictures here of the Mississippi River, and you may have heard of the mud entrained in that flow in the Mississippi River, and you can see it here in the image. You can see how muddy that river looks. Well, that mud is sediment that comes from somewhere. It was weathered from something and then eroded off of where it was sitting, and now is being transported by this river. You can transport it with water. You can transport it with wind. Major sandstorm. I forget where this was. This sandstorm was supposed to be. You can see folks standing around looking at it coming in over the range there. I did forget to put an image here of ice. You can move a lot of big sediment via glaciers. So ice is another big one, but you can transport the sediment with a lot of different media. Okay, a couple of concepts for us to talk through here with sorting. So I put some graphics up here, and then I put these curves on. Now, most of you guys have seen some statistics along the way, and so you know what I mean when I talk about a normal distribution. Every one of these four curves represents a normal distribution. The green here versus the blue. So both of those are normal distributions, but their mean value is in a different place. So we might say that the green one is a bigger particle size on average. It turns out in sediment stuff we'll use median a lot more than mean, but both work. So if you talk about average particle size, the green one has a different spot. But all three of the others, the blue one, the red one, and the orange one, they all have the same average particle size right here in the middle of the graph. So the blue one, though, the distribution, the spread is a lot smaller. It's a lot tighter distribution, you could say. And that, in sedimentology, we're going to call a well-sorted sediment. All right, so let's dig into that and let's look at it. So we've got some sediment here bigger than other sediment in it, but they're not that different. So you might have some big and some small, but they're not extremely different. And there's not a lot of the smaller stuff. Most of it is kind of medium. So that sorting, that's a well-sorted sand. Now let's contrast that with the red curve. Again, the average sediment size is going to be exactly the same here, but it's going to spread out more. It's moderately sorted. And you can see that in the curve here, where the spread is a lot wider for the red curve. And then looking at the sediment, you've got some pretty big stuff here, and then some really tiny ones. There's one right over there on the side, and a lot of different sediment sizes. It's spread out a lot more. So this would be a moderately sorted sand. And then you can go even further. I'll do this with the orange or brown. But again, the average particle size is right there in the same spot, but we have it a lot more poorly sorted. And this time we've got big particles, and then we've got almost too small to see particles. We got everything in between. It's just spread out. And if you look at the spread on that orange curve, you can see how the distribution is spread out over a much broader area. Another thing that we might want to talk about with this is the how it's supported, and we'll talk some about the compaction and stuff. But you see how this first the grains are kind of sitting on top of each other, and we'll work towards an eventual. These are not. So this is a class supported versus a matrix supported model. If you take away the cement and the matrix in between these, they would just fall out of place because they're kind of floating in there. Whereas this is more of a skeletal system where it's all built up. If you take the stuff out of here, it would be loose, but it wouldn't really fall down. And then we'll talk about grading a little further on, how you can have normal grading or inverse, where you can have it getting progressively finer or progressively from the bottom up, from progressively coarser. And that would be graded bedding. But this is all about the idea of sorting our sediment, how clean and how differently sorted it is. Okay, and rounding. So an important thing about rounding is that it is about the corners and the edges, not about the dimensions across the material. So we might consider a cube. Let's say this is three-dimensional and it's a cube, right? So the dimension in the x-axis, how wide it is, let's say this is 2 centimeters in the x-axis and 2 centimeters in the y-axis and 2 centimeters in the z. Well, then we would say this guy is spherical, even though it's a cube. It's a silly term, but sphericity, how spherical a sediment is, has to do with how the x, the y, and the z dimensions relate to each other. If they're about the same, it's very spherical. Versus a piece of sediment that has one or other dimension that is significantly different than the rest. That is not very spherical. As opposed to, that's on my y-axis here. On my x-axis, I've talked about rounded. And you see that it's about the corners. So this guy is very rounded, and so is this oval. Even though it's not very spherical, it's very rounded because the corners are rounded off. And so let's look at actual sediment pictures. You see the same idea. So this is very angular, and it looks like it's like got little points all over it, sticky offy things. And then it progressively gets more and more rounded as it goes, and you get rounded sediments, well-rounded sediments versus angular sediments, and somewhere in between. Okay, and a big deal with sedimentary rocks, especially with the clastic ones, we'll talk about the classes there a little bit, but the idea of powers of 2 for the size differences makes it a little easier to remember, and I'll show you the actual scientific or physical reasoning why we picked some of the barriers. So the first of these to remember is 2 millimeters. Okay, so 2 millimeters is going to be our dividing line between sand and stuff bigger than sand. So what I mean by stuff bigger than sand is a lot of times I'll just call it gravel, but it's everything bigger than sand. Pebbles, granules, cobbles, boulders, all those things bigger than sand. And they are bigger than 2 millimeters in size. Okay, and then I'm going to not circle the ½ millimeter here. It's going to be kind of in between. But I'm going to take, let's see, I don't know if the yellow will show up, so I'm going to use red. I'm going to circle the 1/16 millimeter. That's another one to remember. 1/2 to the 4th. And that's the limit between sand and silt. So think back to when we were doing igneous rocks, and I made a big distinction between phaneritic and aphanitic sediments. And the distinction was that, in the simplest sense, phaneritic grains were big enough to see, and aphanitic grains were not. We're going to use exactly the same distinction here with sediment sizes. So if it is big enough to see, then we're going to call it sand or bigger. And if it's too small, we're going to call it less than sand. We're going to call it mud, and I'll tell you what mud means in a second. But it's less than sand sized. Now, why did we choose 1/16 here? And it turns out, at least this is what's said about it, is that your visual acuity And what I mean by that is the smallest grain size that you can make out with your eyes unaided seems to be 1/16 of a millimeter. Smaller than that, and it just blends together. You can't see where one grain stops and the other starts. You can't make them out as individual grains with your eye. So if they're too small to make out with the eye, then they are not sand. They're something smaller. Now let's talk about smaller. So another one is 1/2 to the 8th power, 1/256th of a millimeter. And that's going to be the division between silt and clay. All right, well, we picked the sand silt division because of where you can see. This one is based on what you can feel. So it turns out your tactile sensitivity is much greater than your visual sensitivity. You can feel things that you cannot see. And this is where the whole idea that you know about geologists eating dirt, this is where this comes from, because we'll take a sediment sample and put between our teeth, because it's a really good place to find the very, very finest silt. If you scrub it between your teeth, it will feel gritty if it's silt, and it will not if it's clay. Clay particles are too small for you to even feel. Okay, one last thing to consider, see if the highlighter here will work, is mud. All right, so mud is a combination term for silt and clay, and it's kind of agnostic. It's like, I don't know, it's mud. I don't know if it's silt or if it's clay, but I can't see the particles, so I'm going to call it mud. Okay, so sediment sizes are very important in this. Okay, a little bit of physics. So think of what you know about stuff falling under the influence of gravity on the Earth. So at the surface of the Earth, everything accelerates downward at the same rate, given that it would be in a vacuum. Okay, so in a perfect system in a vacuum, this should really say gravitational acceleration. The gravitational acceleration in a vacuum is the same for a boulder or a sand grain or a piece of clay. It wouldn't matter. The size doesn't matter. It accelerates at the same 9.8 meters per second squared. But things are not in a vacuum, and that's where it changes, because even though the gravitational acceleration is the same regardless, the frictional forces, the drag forces, the air resistance, all the different things that resist something falling, those are not the same. So if you take a piece of notebook paper and you drop it off of a building, it will fall at a much slower rate than if you take that same piece of notebook paper and you crumple it into a ball first and drop it off, because of the exposed surface area of that piece of paper. And so it experiences more air resistance and drag force, and so it slows down. This is why parachutes work. You increase the surface area that's exposed, and so you increase the drag force and the air resistance, so that you slow a thing down. Well, the same stuff happens with particle transport. And so we get this idea of, well, let's relate it to stream flow velocity. Now, it's really energy, and this flow velocity graph is a little misleading, but I think at the introductory level, it'll be fine to just call it velocity. So let's think about a stream flowing. All right, so let's say this stream is flowing really, really, really quickly. So let's say that's 100 centimeters per second. That's a meter per second. That's fast flowing stream. Well, 100 centimeters per second, that stream can move gravels and maybe stuff even bigger. So it can move those downstream with it. But then let's say you get to a part where the stream is a little slower, right? Let's drop it to 10 centimeters per second. Well, at 10 centimeters per second, it's starting to lose its ability to move the gravel anymore. The gravel is just too big, too heavy for it to keep in suspension at that slow of a rate. Now, at 10 centimeters per second, though, we still think it'll be able to move sand. Okay, so that's how this curve, this lighter color part of the diagram here, is how it works. As you slow that stream velocity down even more, you start to drop things out. So up here at the very, very fast, it's where you're moving boulders and pebbles, and a little further down, other gravel. And then eventually you start, as you slow your stream down anymore, your sand starts to fall out. Now your mud isn't yet. Your mud is still in the being moved by the water, but your sand starts to deposit. But if we slow it down even more, we'll start to deposit out our silt. And then this graph does get to the bottom here. You'll notice it's not all the way to 0 because it's a logarithmic scale. But eventually the clay is the only thing left in suspension. And it's really, really hard to get the clay to settle out. You essentially have to stop the water from moving at all and just let it sit for a very, very long time to get the clays to settle out. And there is some argument that some clays might never theoretically settle out. There are other parts of this diagram that we're not going to bother with in an introductory class, but I want you to think about the idea that this curve splits, and it's really neat in sedimentology how sometimes it takes a very high velocity to initially get those clay minerals into suspension. Once you get them in suspension, they're never coming out. They're going to go as far as the river goes, all the way to the sea. But it took a really high flow rate to initially break them up. And that's because they stick together. It's the surface area effect. And then actually the easiest thing to get moving in the first place might be the sand, even though it drops back out fairly easy. And this is why you get a lot of sandbars and stuff like that. The silt is a little harder to get going because of the stickiness, but once you do, it'll move further downstream. And of course, the gravels are hard to move in the first place. But I want you guys to worry more about this lighter part of the curve, and it's the simpler, faster, can move bigger stuff, and then as you slow it down, smaller and smaller pieces start to drop out. Oh, I should mention too that flow viscosity matters, and I have talked about this entire diagram in the terms of water. But wind matters too, and obviously it takes a much, much stronger wind current to move an equivalent sized piece of sediment, but it does happen. You certainly have wind-blown sand, and you can even move bigger things if you have the right wind conditions. But this bottom of the graph still matters. I mean, we get silt and clay blown all the way across the Atlantic Ocean from Africa and deposited in Florida and in Central America. We think that it comes all the way across from the Sahara Desert. One of the things that I think is so cool about sedimentary rocks is the different structures that are preserved in these rocks. And we're going to talk about each of these as we go, but sedimentary rocks have character. There's stuff going on, and when you look at it, you can read a history in a bit of rock once you start to see all these pieces of it. And I guess to start with, we need to talk about the strata or bedding, and I've already used this concept some. So I actually went back over to our igneous rocks presentations and stole my own diagram from there, but this is the one I used to show the exposure of Stone Mountain, and I weathered away some of these beds or strata above it. Well, I guess now we need to talk about what that means. Strata or bedding, these are our basic units, and they're laid down as beds of sedimentary material. And at least originally, they're laid down horizontally in flat-lying strata. And each of these individual things are going to be our units, our bedding planes. Also put a link on here. It's kind of an online glossary, and you can start to look up things. Anything that I say, if I were to use the term strata and not think to explain what it is, some of these places are good to go to try to define things. And remember that you can always ask me to go back and define things too, is fine. Okay, so let's think through this idea of cross bedding. So think about first for our model down here at the bottom left. Let's just talk in terms of a sand dune, because this may be the easiest way to picture it. So with a sand dune, you've got wind flowing in from this direction, and it's picking up sand and it's moving it up the mound, up further, until it gets to the very top where it falls. And it falls down the backside, and then it'll make these zones as it falls down of slightly different laminae. And at the bottom, they tend to converge into these points. Okay? Make sense so far? Then let's take and let's say we have preserved a block of that windblown sand, that sandstone. And we come back and we look at it, and so we can see these places where you get these points like that. And they're parallel or subparallel to each other, but not to the original bedding. These things will point in the direction that the wind was originally flowing. It works with water also, but wind is sometimes an easier way to picture it in the first place. All right, now let's look at this outcrop over here, and you can see them. So here's our bedding. You can see some bedding here and here, and so this is still nice horizontal bedding. You really see it when you get into the red. But then you get inside it, you get these other structures. Let's look at those. So what's happened here? So there you go. See those down like through that? And that is this cross-bedding structure. So we can look at this sediment package up here on the top right, and we can tell that whatever was moving this sediment, wind, water, whatever it was that was depositing this, the current was moving that direction. All right, so cross-bedding can be important in trying to interpret those environments that I was talking about, starting to read the story in the rocks. Another type of structure that's preserved is graded bedding, where we can get, so if you look at these, you get in A here, we get some really coarse stuff, and they put a quarter in here, and a lot of times you'll see a quarter in things for scale because a quarter is 25 cents, and it happens to also be about 25 millimeters, so it makes it for a nice, easy to remember scale. So if that's 25, let's see, yeah, those sand grains, those might be granules. They might be big enough to be called granules. So I'm trying to decide whether those are bigger than 2 millimeters and they're really close. They're either really, really coarse sand grains or maybe just above sand into granules. And then layer B, you see, is not quite as coarse. So we'll call that a coarse sand. Then we get up into, I don't know what they've labeled. They kind of skip this, but it's a little finer as we keep going up. And then we get into C. And in C, what you're seeing is silt beds. And they often take this really chaotic look to them like this. And it's just muddy sediments that are interwoven like that. So we're getting into the silt there, and I know that we would have to zoom in and see whether we could make out the individual sediment particles there to call it silt or not. But this is a very, very fine sand or possibly a silt. And eventually we're going to get up here to this laminar section with D, and that's most definitely a mud of some sort, silt and possibly clay. But you see how it gets progressively finer, a fining upward sequence. And so your sequences can be fining upward like this one is, or they can be inverted and they can be coarsening upwards. But the whole idea is that they are graded and that they change with some directionality, either getting coarser or getting finer as they go. Okay, ripple marks. Ripple marks are a really cool thing. I have a nice sample of ripple marks, but it is apparently in storage, and I didn't drag it out. Wanted to, but getting to storage with the lockdown is an issue. So this picture, however, is from a good friend of mine, Alan Kressler. I talked to Alan about using his images in this class, and he wholeheartedly said yes, absolutely, and tell them to come look at my Flickr stuff and use these images anywhere in the class is fine. And so I would strongly recommend going and looking at Alan's Flickr stuff. He is a geologist, works for the USGS. It's got really, really great pictures of various geologic concerns, lots of fossils, and lots of cave pictures too, if you're interested in seeing stuff in caves. So ripple marks, so they're really cool to see. I want you to do a thought experiment with me to try to picture them. So think about yourself either standing in the subtidal zone at the beach or in the shallow part of a lake, let's say, like if you're at Lake Weiss or I don't know what other lakes you guys know from the Dalton area. But if you're standing in a shallow area of it, right, and think in your mind about feeling with your toes there, and you'll feel these ridges in the sediment, and that's from the wave action that happens back and forth, and so you get these alternating little ridges like this. Well, so then let's say that you take those ridges, they're in the sediment that's there, and then you bury that under a bunch of new sediment. It preserves these old ripple marks, and when they get lithified, when they undergo diagenesis, it can preserve these structures, and we can find them. If you want to collect some of your own, that good sample that I was talking about, let me know, and I'll tell you where to look. There's a really good exposure in Rome on the bypass. Rome formation is a nice iron-rich red formation, and it makes a good stark ripple marks. I found a little bit of ripple marks in Dalton on the north end of the Dalton bypass, near where you would turn off to go down to the hospital. There is a big Silurian exposure there with some ripple marks exposed in it if you happen to be driving by that anytime soon. We can also preserve mud cracks. So let's return to the lake idea with my thought experiment. So I know this happens with Lake Weiss every winter. They drop the water level significantly. So let's say you're looking at that, and if you've driven across it, you've seen how you get this big expanse of lake bottom that's now exposed and starting to dry out. Well, as the sediment dries out over time, it tends to crack. You see these mud cracks developing. So, all right, so let's picture that mud cracks are developing, but then we get a flood. So when we have the flood, that influxes a bunch of new sediment right on top of these formed mud cracks. And so before the mud has a chance to rehydrate, sediment drops down in all these cracks. And then if it's buried and undergoes diagenesis, you get, down here on the bottom image, you get some of those cracks preserved in a rock, in an actual rock form. There are some beautiful examples of this. If you've been to Cloudland Canyon, there are a lot preserved at the top. I think there's a really good example at, I know there's one in Buck's Pocket over in Alabama, and there's another one, I think, if you go up to the Battlefield Park, not the one at Chickamauga, but the one up on top of Lookout Mountain, right at the edge where you're looking off. There's a really, really good exposure of mud cracks that are preserved in the rock there. And tool marks. And putting these slides together, it made me think about some of our terminology. So I guess tool marks is kind of an unfortunate term. So tool here doesn't necessarily mean something designed by anything with intelligence. A tool is anything that randomly got dragged across sediment. So let's imagine this could have been like a stream flow, and you had a fallen tree in it or something, and it might have a piece that's stuck down and drug along the bottom. And I mean, even though nobody's intentionally using that as a tool, we'll still call it a tool mark. Anything that gouges or makes marks in the sediment we'll call tool marks like that. So those grooves then get filled in by sediment and again preserved through diagenesis when the thing becomes a rock. Another thing that gets preserved is burrowing and bioturbation. So here we have in the diagram, we've got like this is like a worm critter right here, and it's got its burrow made. So if it's going to burrow the sediment, that's going to change what that sediment looks like when it gets lithified, when it undergoes diagenesis. We got like a clam. A clam's buried up in this, and so it's going to make a little spot there, and it's going to change the surface, but it's also going to change underneath. Digging into, this is supposed to represent other layers that were already there. Well, those layers were already there, but now they're going to get disturbed. That's bioturbation, is the disturbing by these critters messing with it. And so apologies to Fangorn from Lord of the Rings. It's not just critters as in animals. Plants do this a lot too. Root structures will stir up these nice, clean, horizontal layers and make them more complex and harder to figure out. And you get these different structures preserved in the rocks. This one over on the far right, I see a lot with the limestones that I deal with, but you get a lot of other structures preserved in the rocks. These are bioturbation structures. And of course, fossils. One of the reasons I like sedimentary rocks is finding the fossils in them. All fossils that you find in rocks are in sedimentary rocks. I guess you can find fossils sometimes preserved in loose sediment as well, but never in igneous rocks or in metamorphic rocks. So let's think about that. This is it's a shark's tooth right here, but it can't be preserved in an igneous rock because an igneous rock was magma, molten, and then solidified. So, well, the fossil would be gone. It would have been changed into something liquid and then just precipitated out as crystals with everything else. Or a metamorphic rock, which we're going to get to next, requires recrystallization, and this entire shark's tooth structure would have been just obliterated if metamorphism happened. And down at the bottom, you have a fish, probably Green River. Just looking at it, I would bet this is Green River sandstone. It's famous for its fish fossils. You can find these all over the internet. There's a museum if you happen to go out there. And then over here on the far right, this is a really neat one. I love these. These are called blastoids. So you can see this is kind of like a sea lily. So what happened was you had a structure, has a root structure and then a thin stalk. You don't see it in this picture, but there's a thin stalk that would hold this structure, which is the head of the blastoid, hold it up off the seafloor. And so these, you can see the plates here, triangular shaped plates that would open from the head and let out feeding arms that would pull in. It's a filter feeder, so planktons or other suspended material too small for you to see that it would feed on. So this is kind of like a sea lily in the way it works. It just pulls in stuff from outside like that. Also a neat thing about it, this top image, you can see it. Look at these triangular lobes. We've got a suture there that makes a triangle. So 1, 2, 3, 4, 5 arms. And then if you see a cross section of the stem, it also has a star-shaped, 5-pointed star-shaped pattern in it. And that tells us that even though these are anchored to the seafloor, because of the fivefold symmetry, we know that they are related to other echinoderms. We classify them with echinoderms, which are the starfish, because those are also 5-pointed. Okay, and I have used this term diagenesis multiple times. Okay, so what's happening with diagenesis? This is the process of turning sediment into sedimentary rock. Let me illustrate the difference of that. Think in your mind of sand. So pick up a handful of sand. What happens? It'll run through your fingers. It doesn't hold together. In the other hand, pick up the same amount of a sandstone. Well, that does stay together because it's lithified. It has undergone diagenesis. And that's what holds it together. Let's look at what has happened. So initially, this is our sand. It gets deposited. And there might be water in between the grains. There might be a little bit of mud or even some biological material in between the grains. And so over time, the water and other stuff kind of gets pushed out as the sand starts to settle down. It settles and it compacts. And as it does, these pore spaces, the pore space is what's in between the grains, the pore space is decreased. It's compacted. And then eventually, cement, and this doesn't have to be cement in the form of calcium carbonate, though it can be, like what you would see. Calcium carbonate would be a typical mortar that we would call cement in a building. But this can be of a lot of different mineralogies. A lot of times it's also silica, like we would think of being quartz. It can be iron oxide a lot of times. A lot of different mineralogies and chemistries that it could be. But that will start to precipitate in the leftover pore spaces after compaction. And that's what holds your sediment together. A couple of images down here at the bottom on the left. This is a thin section of mineral where we have taken a rock. This looks to me like it's an oolitic limestone. Maybe calcite chunks here with the light blue color, and then around the pieces are other pieces of mineral, and in between you see these opaque in some cases, or probably mineral grains here. What a thin section is we'll take a piece of rock and glue it to a slide, and then grind it down so that it's so thin that light can actually pass through the rock layer, and as it does, it twists it into these colors. And it's a way that we analyze what the minerals are in a rock. And you can see how this has these concentric rings that look like kind of like a tree ring building up around this original piece in it. And then here's a micrograph. And so to give you an idea, micrograph is a picture taken through a microscope. 200 microns wide. So that whole scale bar down there is 200 microns, 0.2 millimeters. So this is really, really, really zoomed in. And you can see the little pointy crystals that are growing off of the sediment surface. There's big sediment chunks here, probably sand, here, and here. And then all these little bitty crystals grew off of them. And as they grow into the pore space, they start to grow into each other and lock. And that lock between those, that's your cementation. That's what's holding that sandstone together, is the cement that's grown on the outside of those grains. So how we classify sedimentary rock. And here I have two major classes of, and I would like to put quotes around chemical here, chemical versus detrital. And detrital I will also often call siliciclastic. Okay. Most of what we've talked about with sedimentation processes and everything is going to refer to the siliciclastic rocks, the conglomerates and sandstones and shales and stuff like. And then chemical is kind of a catch-all term, but it also includes biological, and that's why I wanted to put it in quotes, because it includes the idea of limestones, which are built up entirely sometimes by organisms. So chemical leaves a little to be desired, and it can be entirely built up by critters. So, but we're going to divide it into classes. I know that Dr. Brenda, we're using for the lab, he has a separate for organic, for coals, and then I think he does end up putting the limestones in chemical, which again is problematic. But really, I guess what I'm wanting to do is divide siliciclastic from other. We're going to talk about how the siliciclastic rocks form this idea of facies. So another thing we need to talk about with this deposition is the idea of facies. It's the way you say that word. Sedimentary facies, okay? And I'm going to mix in siliciclastic and limestone here. So really, 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 really stripped down, simplified model here. But it gives you kind of a conceptual framework, okay? So on the one end of the siliciclastics, we're going to ignore conglomerates and anything like that. We're just going to talk about sandstone. And we're going to talk about shale all lumped together as if it's all the shales, the mudstones, the claystones, all those things lumped together. And then the limestone facies, which is not siliciclastic anymore. So let's think about energy. So this is like a cross section of a beach, and up here you have where the waves are hitting the shore. So think about the energy involved. That's a very, very high energy environment. So we're going to say that the only thing that can fall out of suspension here is sand. And if you think about it, if you go down to the beach in Florida, that's what you'll find is right at the shore, you find only clean sand because that's the only thing that can get dropped by the water right there because there's just so much energy that everything else gets held in suspension. But as you go further away from the shore, the wave action, the water gets a little deeper and the wave action gets a little less energetic. And so you get finer and finer sand out until you get, eventually, you'll get into a muddy bottom area where we're going to call this our shale facies, where the stuff that's being deposited is the finer grain siliciclastic, the muds, the silts and the clays. But if you go far enough offshore, you get where you've even run out of your mud. And so your water is just clean at that point, and there's no more siliciclastic to deposit. That clean water is where your coral reefs like to grow. And so remember that our limestone is built of fossils mostly. And so our coral reefs are a really, really good analogy for how the limestone facies develops. You get corals, you get shells, you get only stuff like that. And even though there can be some of those up here in the high energy, that's all there is in the limestone. It's just the carbonate skeletons. So we're just going to simplify that out to we have a sandstone facies in the high energy, then a shale facies in the lower energy, and then once all the other sediment is gone, eventually we get to the clean limestone facies. And so those would be the rock types that would be deposited. But now let's look at what might happen. Oh, I'm going to color in the limestone with a different pattern. You'll see that block pattern colored in the limestone a lot because it tends to fracture in those block patterns. But so what would happen if we were to, let's say, I'm going to extend the land here a little bit and raise the sea level. So there's a lot of talk nowadays about rising sea levels. What happens to the sedimentary facies? So there's my raised sea level from the previous. Well, that highest energy environment where we are depositing the sand that's going to become sandstone, that's further uphill now because we raised where the water is impacting on the shore. And so we can deposit sands further uphill. And then, of course, followed by the sands, further out in the water, we get the shale facies. And eventually, when it's really clean further out, we'll get a limestone facies. But then that sea level fluctuates over geologic time. It'll go up and it'll go back down. So now let's play with it a little bit and let's lower the sea level again to a lower sea level stand. And again, we'll deposit our sands closer into shore, followed by our silts or muds, and that's going to be our shale facies, with our carbonate facies or limestone facies further out to sea where it's nice and clean. And so you get that developed. And so what happens is this gets deposited and eventually lithified into rock. And so we'll come back later and we will find a section of rock that develops through that, like Pigeon Mountain. And we'll find limestones, we'll find shales, and maybe even some sandstones if this is far enough out. And we're back into limestones again. No telling what might be on top here if things change entirely. But that's how you get the different rocks developing in facies offshore and eventually exposed as rock systems that we can look at on the surface. Just to talk about our different types of sedimentary rocks, conglomerate is a siliciclastic rock, and our average grain size for this is going to be over 2 millimeters. So when you see these big pebbles and gravels and stuff like that cemented together, that's going to be a conglomerate. And then a little lower energy environment, we'll get a grain size between 2 millimeters and 1/16 millimeter. So 1/16, remember, is that visual acuity limit. So I can see the individual grains. Yep, okay. And they're not giant like the gravels. So this is all sand, and this is a sandstone, again, siliciclastic. And now we're further offshore in that shale facies, and I'm going to divide it up here a little bit. And don't worry about this too much. This is just siltstone is when it's in a blocky form, and shale is when it's in this more what's called fissile form. And you can kind of see how the layers would break loose in that. That's called fissile. And you can break them off in layers like that. Most of the mud rocks that we find in this area are fissile like that, and they're shales. And I tend to use the term shale for the whole set of, but technically, I guess I should try to use mudstone more where it's unsure whether it's fissile or not. And I haven't spent much time on evaporites. They don't occur in this area, and so we don't see very many of them. But an evaporite is anything that chemically precipitates from solution, and that's from solution, like dissolved, as opposed to suspension, where it is just suspended in the water. And the analogy for that usually is if you take and you mix up muddy salt water. So we've got some ocean water, and we're going to mix up some mud in it. The mud is in suspension, and if you set that glass of water down and just leave it alone, sands will fall out immediately, followed by your mud. Eventually will settle out at the bottom, but the sodium chloride in it is actually dissolved. The sodium ions and the chloride ions separate from each other. They will never settle out. Okay, well, if they never settle out, then how do we get these deposits? These pictures here from the Dead Sea. So what happens is, yes, they are permanently in solution, but you can evaporate the water. As you evaporate the water, the sodium and chloride ions are left over, and they eventually find each other again, and they form these salt deposits. But because it's due to evaporation, we call these evaporites. So we got salt crystals forming here on the shore of the Dead Sea, and then eventually you get these layers like this, and they build up over time. And eventually I think they tend to make like caves and stuff where they get hollowed out, and you can like hide scrolls in them or something like that. Also, there's another form called rock gypsum. You can do this. So these pictures here are all of halite, the mineral halite, sodium chloride, maybe some sylvite in that, or rock salt. But you can also do this with gypsum with calcium and sulfate. That happens about as much as halite does. And then, of course, my favorite by far, not even close, is the carbonates. Limestones, dolostones, stuff like that. So here's another one of Alan's pictures of a cave. This one's up in Tennessee, I believe. And these layers, these are limestones. And they're great for cave forming. And these are thin sections of. Down here on the left with the pink is limestone thin section. And so you see these little structures. Once you get down into really, really thin microscope pictures, you can see the pieces of. And even if you can't see these with the naked eye, you probably would not be able to. The fossils are there even at the lowest level. And then we've talked a little bit about dolostone, and I told you not to worry about trying to differentiate dolostone at the entry level here. But where limestone is formed from calcite and readily reacts with our cold hydrochloric acid, if you use a dilute hydrochloric acid with dolomite, that's the mineral that makes up dolostone, it doesn't react actually. Now if you heat it up or if you powder the dolomite, it will react. And that's how you tell the two apart in practice. But if you make these thin sections that I've been talking about, and again, this is another one about 5 microns thick. So with the calcite, you see fossil structures and you see mud bits ripped up and stuff. But then the dolomite, look at that. Do you remember when we fractured the minerals and we saw those cleavages? Well, what you are seeing here is actually cleavage rhombohedral cleavages of dolomite inside the mineral structure down at the submicron level. And that's diagnostic of, that's the real way we'll tell dolomite from calcite in the rocks, and therefore dolostone from limestone. Of course, you don't have to worry about that, but now you know a little more what's going on inside those rocks when one of them will react with calcite easily and the other not so easily. Cherts are an interesting class of rocks. My take on cherts is currently in flux. It just so happens that I live on a hill made of chert, and so I end up thinking about this stuff a lot. So the typical way it's presented is that they are a chemical sedimentary rock. I think though, so when you make the cross section, you find that they are made of these guys right here. These are called radiolarians. So they're a type of creature that are way, way, way too small to see. And they make shells, though, and they can float around in the water. They make their shells out of SiO2, silicon dioxide, just like quartz. And so when these things die, they can settle to the bottom and make these massive, massive chert deposits that we find, maybe. And this is where my thinking on this is evolving right now. But I'm going to say maybe quartz. And the reason I'm saying that is that the question is whether or not this is crystallized into quartz crystals or whether it is an amorphous form of quartz when it is deposited or when it's in the radiolarian shells. But you can certainly find crystalline versions when you find the chert in the outcrops. And all three of these pictures over here are from what's called the Somerville chert. And if you drive over to the Somerville area or south of Lafayette in Walker County, you find a lot of this deposit. And it's really pretty. People come from all over the place to collect there because of the Somerville agate. Agate is just another term that gem people use for chert. Chert is the rock type, and banded chert or banded agate is it's easily found in this area. It's really pretty sometimes, but in it you can see up here on the top of this one you can particularly see, and then on this one once you start looking, are definite quartz crystals. So we get cryptocrystalline when they're in the form of the radiolarians, but over time they maybe recrystallize chemically into good quartz crystallization. You get some really good, pretty forms out of them. And then finally, let's talk about coal. This is, I think, the only one that Dr. Brande puts in the bio sedimentary. I would have probably classified limestones in biosedimentary, and maybe even the cherts. I think there's an argument for putting the cherts there with the radiolarians. But coal is definitely the remains of organisms. But unfortunately for the cartoons, it's not usually dinosaurs that make coal. It's usually plant remains and bacterial remains that make coal and oil. So here's a chunk of anthracite coal. It's all carbon. You do have different grades of coal. Anthracite's the best. Then bitumenite, lignite is really, really bad coal, and then peat. Peat is, well, maybe it's still moss and maybe it's coal, but somewhere in between. So remains of organisms, and in fact, you can find good fossils in coal. There's an old coal mine on top of Lookout Mountain called the Durham Mines, and you can actually go out there and find your own fern fossils like this one. I have a few of these. You can find other fossils occasionally in it, but it's mostly fern fossils that you find here on Lookout. Other places you can find other fossils in the coal, but course, coal is an important economic mineral, maybe becoming less so as we're trying to shift away from a carbon-based economy. And so there's a lot of talk about how much coal we should be using and how much we've used in the past and changed our environment drastically with it. All right, well, that's our classification of sedimentary rocks. And see you again next time.